All right, we'll go low tech and just put the mic lower. All right, so quick reminder, lab this week is the LO1 second chance. So if you did not get the learning objectives for both the interview and quiz 2 weeks ago, you'll show up to lab this week and the TAs will be ready to give you your second chance. You'll get another quiz, another interview, same structure as it was 2 weeks ago. And I want to see everyone passing it this week, especially since last week I keep hearing that lab attendance was pretty low and students weren't paying attention to it. I hope that means that everybody's solid on this stuff now, got your results, reviewed it, and you're ready for that second chance. So everybody should be getting that learning objective done. A reminder, you can't earn the application objective this week. There will be no chance to get the application objective on the second chance quizzes. So don't show up expecting to try to get another chance at the application objective. If you got both learning objectives for the quiz and interview, there's no reason for you to go to lab this week. So if you do have both learning objectives, quiz and interview for LO1, you shouldn't be in lab this week. The TAs won't have anything for you to do, and you can safely skip it. All right. And then next week, of course, learning objective 2 verification. We're already on the next one. So any questions about this, any questions about logistics or anything before we get into a big, meaty polymorphism example that's going to take up all of lecture? We're all OOP experts. Yes. Oh, the makeup's not even OOP. We're all memory stack experts. I mean, LO1 at this point should be, the quiz should be pretty simple because the memory examples that we're doing in lecture, including today's, are quite involved. So if you can follow along with the ones we're doing now, you should certainly be able to knock out that LO1 quiz on your second chance. Will we get a review during lab like we did previously? Depends what you mean. So we're in a rhythm now at this point. It's quiz and interview, review, second chance quiz and interview. Quiz and interview, review, second chance quiz and interview. So we're in a rhythm, we're in a little flow right now. The only exception is LO4. It's quiz and interview and then second chance right after. Just because we run out of weeks in the semester, there's no room for review. So for LO4, I'm going to do review during lecture in that week. So I'll go over the quiz solutions or at least some sort of equivalent. I can't do every version of the quiz, obviously. But I'll do maybe just pick a version of the quiz or do something similar to the quiz and go over it in lecture for the review for LO4. But yeah, we're in a pretty good rhythm at this point in the course. Everything works on a 3-week cycle. So every 3-week section of the course is going to be the same structure, just different content, just another learning objective. But the flow we should be getting in a rhythm at this point. Save. Can we get a Google Doc to practice LO2? So like I see what you mean. The review before the first LO1 quiz and interview, you're not going to get something like that for the other ones. That's just because we have an extra lab before there are any quizzes that went out. So that's what we decided to do with that, a pre-review. After this, it's going to be post-quiz review. So if you didn't do well on the quiz, you can go to the review to get more review. Say, for example, we missed the AO on all the quizzes. Can you make up all the AOs on the final exam? Yes. The only kind of exception, the kind of caveat to that is if you're going into the final exam needing 4 application objectives, you might not be able to do it in 3 hours. Maybe you can, maybe you can't, but you certainly have that opportunity to do all 4 during the final exam. But it might not be timed to be able to be reasonable to do in 3 hours. But if you can, Yeah. My gut, oh, no, let me not go there. Is there any way to practice memory examples or only the examples done in class? I mean, you can take any program, any Scala program, and just practice writing the memory diagram. Honestly, if you showed up to my office hours and said, hey, here's this program, I sketched out the memory diagram, I think this is right, can you give me some feedback? I'd be thrilled to do that. I would be so happy to be able to do that, to give you feedback like that. Because most of office hours are, my code doesn't work, help fix it. To get anything that breaks that cycle, I'd be really happy to go through your memory diagram. So show up to office hours if you want the solutions. If you want other like walkthroughs of memory diagrams, it's lectures, and also Paul's lectures. Paul does similar but not exact examples as I do. So checking out Paul's lectures in sections A and D as well can give you a more variety of examples. So you always have those ones available to you. But other than that, yeah, lectures are your biggest source of practice memory diagrams. Yeah, like the week 3. So like week 3's lab, you won't see something like that again. But the doc at the top of the course website, this is worth mentioning just in case there's someone out there who hasn't seen this yet. This memory diagram reference, this is a live document. This does get updated. Paul updates this with more examples. And we do have an inheritance example on there. So you can continuously refer to that for another source of examples as well. I like your beard. You can finally see my beard. All right. I got to get started on these slides. Nicholas, can you let me know if there's something that needs my attention there? All right. So polymorphism, today's entire lecture is an example. Hopefully this one, at least this phrase makes sense to you, even if the application in your code isn't quite fully gelling yet. But the fact that an object inherits a type, it can be stored in variables of that type. This will be the last time I flash this. I don't know, maybe I'll flash this again on Wednesday, but hopefully you're getting that phrasing anyway. The implications are many and vast, and that's what we want to explore today. And also, as we talk about the state pattern is an application of both inheritance and polymorphism. We need both of those topics to enable the state pattern, so we'll continue to reinforce polymorphism through that. Today, I want to go through this example only. This is what we'll do all day. So I'll give you a few minutes to take a look at it, think about how you would do the memory diagram of this thing. I think I got my font size fine. I'll walk to the back of the room again and read some chat while you look at this. I want to make sure my font size is good. I'm at a point in my life where I care about font size. It's something I have to wrestle with. Ooh, I can read the hell out of that. Yeah, I think the quizzes will still have 3 questions. The rough idea, I don't think this is leaking anything that you couldn't deduce on your own, but just to be explicit about it. 3 questions. There are 3 topics: classes, inheritance, and polymorphism. So 1 question on each is roughly how it'll roll. It roughly follows the 3 weeks of the learning objective as well. Week 1, we introduced classes, started talking about the heap memory and stuff. Spent 2 lectures on inheritance, 2 lectures on polymorphism, and then 2 lectures on state pattern, reinforcing the 2. But the 2 big topics there are inheritance and polymorphism. And state pattern is strictly a way to reinforce that content. State pattern, I wanted to check this. I'll take down the code just for a second here. Just to refresh myself on my own wording. But in the syllabus, I don't think I mentioned the state pattern. If I did this right, I didn't. Yeah. So state pattern isn't even a learning objective of the course. There's nothing in there that says, we're going to ask you to use the state pattern. It's implicit in right that you can change the behavior of a program based on the type of an object stored in a variable, which is basically another way of saying the state pattern, which will make more sense when we talk about it, but not explicitly the state pattern. So the big topics are classes, inheritance, and polymorphism. That's what we want to test you on. So those will be roughly the 3 questions on the quiz. The quiz for LO2 is going to take a lot longer than LO1. I talked about this briefly last lecture, but it will take a lot longer. LO1, there's only so much we can ask you to do on LO1 without just being tedious. The only topics were unit testing, which doesn't show up on the quiz anyway, and the stack. So all we could do is say, do you understand how variables go on the stack? Do you understand how stack frames go on the stack? And do you understand how code blocks are treated on the stack? That's all we can ask about. And then code blocks have the implicit variable scoping properties. I mean, there's not much we can do with that. With LO2, I mean, I struggled to keep the code down as much as I could here, and I removed all the blank lines to fit it on a slide. Like, there's only so much I can do. It's going to be the same thing for the quiz. We can only make these so simple before they're not testing inheritance and polymorphism anymore. So we'll expect to take a lot more time on the quiz next week. So just a heads up on that. Are the LOs for the interview and the quiz the same? Do you need to pass both? You need to pass both. So each learning objective, refer to the syllabus, but I'll give a brief reminder. Each learning objective has 3 parts: read, write, and explain. The read is the quiz, the write is the project, the explain is the interview. You need to pass all 3 parts of each learning objective to earn that learning objective. So you need to pass both the interview and the quiz, the learning objectives. The application objective on the quiz, that's optional. That's where you're working towards your A. And if you didn't get that, you can still make it up on the final exam. Okay, everyone had a chance to look at this? Actually, the first thing I have is a question for you anyway, so I'll give you a little more time to look at it and think about it before just giving you the answers. So my first question is how these objects will be created. I'm going to create all 3 of these objects, put them all on the heap, all the stack frames and everything in one slide. So just giving you a heads up on that. This is inheritance. We've done this already. This is creating objects with inheritance. So it's a little more involved, but we've talked about creating objects, constructor calls and stuff. We've done inheritance. I don't want to spend the whole lecture rehashing that, so I'll let you take a look at it, take a stab at it. I'll go to the slide. I'll briefly explain it, hit the key points, and then if there are questions, I'll be happy to answer them. Otherwise, I want to get on to the polymorphism part, which is where we're taking variables of one type and storing them in, objects of one type and storing them in variables of another type. That's the juicy part of today's lecture. That's what we want to talk about, especially when we get right here. Total weight. Ooh, how's that going to work? Which I'd be willing to bet, I say this a lot for programs like this, I'd be willing to bet that the vast majority of you, maybe with the exception of what to do with super.weight, other than that, I think the vast majority of you would be able to tell me what's printed out right here. I think you could figure that one out. The question, what we want to talk about and reinforce today is how the hell does it all look in the memory diagram, because that's what you have to write on your quiz. You have to write every detail of that memory diagram. Show me that you know exactly how this program runs in the computer, not just kind of guess your way to what's printed out at the end of the screen. So that's what we want to focus on. Okay. So let's start populating this thing. So this, like I said, I'm not going to break this down into individual slides. We're just going to put these objects on the heap. So hopefully you looked at this, you thought about it, and you came up, either wrote it yourself or at least thought about it in your mind that this is how it would roll. The big thing is when we have inheritance, we're going to call a constructor, put that frame on the stack for a dodgeball. When we call the dodgeball constructor, the first thing the dodgeball constructor does is call the game object constructor. So we're going to say extends game object. That creates another constructor call for game object for the superclass, and that constructor is going to do everything that it does. So each constructor is going to get a reference to the object that's being constructed, but each one is going to add its state variable, size in this case, and then base weight in the game object's case that it does. So base weight got the value 0.0. So base weight 0.0, base weight 0.0, since it's a constructor parameter, becomes a state variable of the object that's being created. Same thing with health potion. We say new health potion of 6. Volume gets 6, a reference to the object that's being created. Health potion calls the game object constructor. Base weight equals 3.0. So we get a game object constructor call, reference to the object being created. Base weight equals 3.0. It's a constructor parameter, so it becomes a state variable. And then after the game object constructor returns, we're going to go into the health potion constructor again. This call returned, that stack frames off the stack, and then we're going to run all the code outside of the methods. We declare a value mass per volume with value 7. It's declared outside of all the methods, so that also becomes a state variable of the object. And then when we get to player, player is just a class with no inheritance. Technically, it does implicitly extend any ref, but for our memory diagrams, we just don't care. We don't care about any ref in that constructor call. So player, create the constructor, a reference to the player being created. And the new thing, what does super do? Good question. What's the colon thingy? Excellent question. We're actually going to talk about both those things in this lecture. Those are both big points. So the one big thing that's shown right here that we haven't talked about yet is linked lists. Now, linked lists, it's a topic for LO4. That's where we're really going to test you on it. We're still not going to put linked lists in the quizzes. So you're not going to see linked lists on the quiz. And you won't have to draw linked lists on the heap. I'm going to show you it in this example, so you have a bit of a foreshadow with that of how linked lists work, so we can see how they're going to be represented. Because we use lists a lot in our programs, I want to show you how linked lists are going to work, even though you're not expected to draw the linked list yet, not until LO4's quiz. That's when you're going to have to do this. So when we create a new player, we call the constructor. There's no parameters. Nothing happens there. Then we run the code outside of all the methods. We create a new variable named inventory, which is an empty list. The empty list we're going to represent like this. This box is going to be a reference. And this is the notation we're going to use for a reference that refers to nothing. It's an empty list. There's nothing to really refer to. List will be an object on the heap. But right now, we have a reference to no objects. There's nothing in this list, nothing to see. It's referring to nothing. When we get to linked lists, we might have this be a reference to null, which is a special value, which means nothing. Yeah, super is a reference to super. It's not a reference. So a little nuance point, super, since it's being asked in chat, I'll jump ahead to super a little bit. Super isn't a reference to any objects, but it does kind of conceptually refer to the parent class. But I'll try to not use the word refer or reference because it's not a reference to an object on the heap, but it is a placeholder for the super class. So this is like saying game object, call game object's weight method. So this is a way where we're going to access any methods that we overrode. So we overrode the weight method, but we still have access to the unoverridden, to the superclass's definition of that method using super.weight. That's going to call game object's weight. Yeah?
So if you overrode toString, could you go super.toString?
Yep. Yeah, you can do the same thing with an overridden toString. Actually, I wish I did it in the inheritance example. I actually updated the repo, so health potion calls super.toString and then appends the volume of the potion to the end. So this is how we draw an empty linked list. And we're about to add things to that list. I'll get to the other answer, what's that : which is review. Hopefully you've been using : in your homework. I don't think you can get away without it, unless you've been appending. I guess you could use : plus. So the person asking about : maybe that is. I think that's a safe assumption. So you do your list : plus and then some element to append an element to the end of a list. : is the syntax to prepend, to add an element to the beginning of a list. So I'm adding object to the beginning of this list. Instead of saying this.inventory : plus object, that would add it to the end of the list. You've had to have used at least one of those two in your homeworks, both homeworks so far. Okay. So now let's get into some juicy stuff. We have pickup that takes a game object. We don't have any game objects. This seems like a problem. Hopefully not, because if you pay attention on Friday, you know this is no problem at all. This takes a game object, a variable of reference to an object of type game object. We called it with a variable storing a reference to a dodgeball of type dodgeball. So ball has this reference 350, refers to an object of type dodgeball. We just called it with a method pickup, which takes something of type game object. This seems like a bad thing. At the beginning of the semester, I said, Scala, your types, they have to match. It's strongly typed. You can't do this. You just can't do that. Your types have to match. They can if the object inherits from the variable. So if an object is a certain type, it can be stored in variables of that type, and that includes across method calls. So if the parameter is a specific type, we can call it with another type as long as this type extends this type, which in fact it does, of course, in this example. Dodgeball extends game object. Dodgeball is a game object. So we can call a method that takes a game object with a reference to a dodgeball. Perfectly legal. That's polymorphism. This right here, when we call pickup that takes a game object and give it a dodgeball, we just used polymorphism because we took an object of one type and stored it in a variable of a different type, of one of its supertypes. That's polymorphism. We just used polymorphism. We're about to use it again. Right here, we have a list of type game object. We can't put a dodgeball in a list of type game object. That's not allowed. The types don't match. But dodgeball extends game object, so we're perfectly allowed to do this. We can store dodgeballs in a list of type game object because dodgeball extends game object. Dodgeball is a game object. Perfectly legal, perfectly fine thing to do. And we got to talk about some linked lists. So this syntax, usually it is confusing when you first see this. Let's crack this open a little bit and explain what's happening on the heap when we use this syntax. And especially the question, which hopefully was addressed enough that wasn't an issue, isn't an issue anymore, why we have to reassign this to our variable. We do have to change our variable to do this. So our variable, it was referring to a reference to nothing. If we want this variable inventory to refer to something, we're going to have to reassign it to a reference to something. It doesn't refer to anything at the moment. So we have to make it refer to something more meaningful. This : operator is going to give us the first element of a new list. That's what it's going to return, a reference to a new list. That list that's created is going to have two values. One, which I named value. I'm reusing that thing. Two state variables, value and next. Value is the value stored at that portion of the list. In this case, the only element in the list is going to be a reference 350. I missed my arrow. I promise it'll appear on the next slide. I hope the next slide, but one of the slides. I know I have that arrow. That reference 350 is going to be stored in this list as its only element. The next value of the list is going to refer to nothing, and this portion of the list will be somewhere in memory, somewhere on the heap. Now, what I just explained is this part of the code. We've created a brand new list in memory, storing that value and referring to nothing because we prepended this object reference to the empty list. So the empty list was nothing, and object was a reference 350 in this case. But with just that, we haven't changed the player's inventory at all. We haven't actually changed the player's inventory until we reassign to the inventory. We want to say this dot inventory equals a reference to the linked list that was just created. So we want to update that to be a reference to 120, which is a reference to that portion. We'll end up calling them nodes in Learning Objective 4. That portion of the linked list, we're going to refer to that, and now we can actually store our linked list in our inventory. Oh, I thought I got rid of the penalty late days. Those are still showing up?
Yes.
Are they showing as zeros, or are they actually showing as non-zero numbers? Is non-zero? What was it? Non-zero numbers? All right, I'll have to look at that again. I thought I fixed that for everything. Okay. Yeah, I'll have to look into that. See, there's my arrow. How did I miss that on one slide? Hopefully that's my only typo. I looked over these ones. I'm pretty confident I don't have mistakes on this one. But one arrow missed. -1 already. So each linked list node is going to refer to either the next node in the list or to nothing if it's the last node in the list. So this is where we get the linked part of linked list. A linked list is elements all over the heap that refer to the next element in the heap. Keeps referring to the next one, referring to the next one, referring to the next one. And then once we see a link in the list that refers to nothing, we know we've reached the end of the list. So let's do the same thing with potion. Let's add potion to this list. Again, a list of game objects. And we're about to have a health potion and a dodgeball in the same list. Whoa, that's something we wouldn't be able to do before. Polymorphism. Ooh, baby. So now, and the arrows are going to get messy. I think this is the last example where I'm actually going to have the arrows. It's just getting way too cluttered. By the time we get to the end of this, it's like arrows just flying all over the friggin' place. So especially when it's color-coded, I think it's clear enough that this is a reference to the dodgeball. This is a reference to the health potion, etc. So I think I'll cut out the arrows. I might wait till the end of LO2 because we still want you to draw your arrows and your quizzes for LO2 to make sure we know 100% you know what you're talking about. All right, so we're going to repeat this for health potion. Right here, in this stack frame, object is the reference 200. This is the reference 480. This dot inventory is 120 at that point. So we're going to reset this dot inventory to object 200 prepend, which is going to create a new linked list object. Prepend that to this dot inventory, which says this new. We can kind of read this as this new linked list object we're creating. Its value should be object, and its next should be a reference to this list. So we create that on the heap. Value is 200, which is object. Next is 120, which is a reference to this dot inventory at that time, a reference to this section of the linked list. And then at that point, we haven't really done anything meaningful yet until we reassign it to this dot inventory. We want this dot inventory to refer to the new head of the list, or first element of the list that we created. And now inventory, we can see how the linked list structure is starting to come together. Refers to at 800, we find the value 200. That refers to 120, which has the value 350, which has a next of nothing. So that's the end of the list. So our list contains a reference 200 and a reference 350. When we iterate over the list, those are the two values of the list in that order. I've been putting off linked lists for a long time. Paul showed linked lists on week 2. So I had to catch up a little bit and show some structure of a linked list. But again, LO4, that's where we're going to go way in depth on linked lists, way more than we have here. We'll have all kinds of memory diagrams with lengthy lists and prepend and append and all kinds of fun stuff. That's all I want to talk about lists for now. When we iterate over this list, which we'll do right here, we're going to iterate over 200 reference, next, and then 350. Which by reading the code, I'm sure you can figure out that that would be the functionality, that would be the behavior. This is how it looks in memory. Do linked lists need to have value and next as the parameter names? No, they can be named whatever you want. If you want to implement your own linked list, you can name those variables whatever you want. But they will functionally have, like, this is the value that's stored at this section of the list, and here's a reference to the next section of the list, the next link in the list, if you will. So they'll functionally behave like that. But yeah, if you want to name them puppy and kitten, whatever, it's whatever. I don't even think they're named value and next in Scala in the internal list. I forget what they're called, but I don't think they're value and next. Maybe next. I think next is pretty common, but value, I think it's, I don't know. I'm just making things up. Do we do memory diagrams after 116? Probably. You will. So memory diagrams are going to be in 220. I believe they will be in 220 next semester, starting next semester. So I think you will see memory diagrams. I hope you're asking because you love memory diagrams so much, right? These are really helpful, by the way. We haven't always been doing these. I did. This is the first semester we're doing memory diagrams with this specific format. I've always done memory diagrams, but like in each course we just kind of make up however we do memory diagrams. Like memory diagrams will be in 220, 100%. Memory diagrams were always in 116, 100%. But now they're being standardized to this format. You should see this format starting next semester. Instead of you get whatever the hell I make in my slides in 116 and then whatever Ethan puts in his slides in 220, there shouldn't be a rough transition. That's our goal. So we're starting to standardize this. And then we even want to add this in 115 if that floats your boat. But overall, we all see this as a positive thing. It may be confusing. There's a lot going on, I know. But without memory diagrams, all of this is still going on. You just don't know that it's going on, and you don't necessarily understand how that's working. With the memory diagrams, if you have to draw all this out, you're going to know the hell out of how your programs work. You're going to have way less bugs when you're writing your code. If you know that this is how a linked list works and you can draw all this, you're never going to forget to reassign to your linked list, and you're going to understand why that's important. That's going to make writing your code a lot easier. So I made a lot of assumptions there. If you want to follow up, that's fine. Paul did show a victim of memory diagrams. Memory diagrams are the best thing in the world. Come on. But I hope you'll agree that it helps to visualize how the programs run. But I don't know. We can have that debate. I'm willing to have that debate. But they are here. They're a part of your lives now, whether you like it or not. And it will help you learn this content, even if you didn't want to learn it that far in depth. Kind of why you're in college, right? To learn things in depth. If we were just doing a surface level scan of things, I mean, you can just read the internet and figure that stuff out. But this is going to be harder to find just Googling how's the heap work. You might not find this stuff. But I don't know, for what it's worth. But anyway, we can have long debates on that. I'm not going to take up more lecture time on it. So we picked up both of these items. I will defend memory diagrams to the death, by the way. Even if it's not this format, the format I'm flexible on, but I will defend. You have to understand what's happening on the stack and heap, or else you don't really understand your code. All right, so let's get into this thing. This is the crux of what we want to talk about, the last method call, which is going to take quite a while. We got a lot going on here, and this is where we're really talking about polymorphism. We definitely used polymorphism. We stored a health dodgeball and health potion in a list of type game object and called them with a method that takes game objects. But we haven't seen any benefit yet. Now let's get the total weight of our that our player is carrying by leveraging polymorphism. So we know the player is carrying a dodgeball and a health potion, but we're going to make one call to total weight and get the sum of the weight of all of those items. This is very similar. This should be feeling familiar to task 2 in the project of asking an item, what is your price? This item has lots of modifiers. Those modifiers are sales tax, bottle deposit. Any mix of those three could have multiple of each of those. We don't care. We're just going to say, what's your price, what's your tax? And the item is going to go to the modifiers, loop through the modifiers like we're about to do here, call the modifier methods, and get the final price and tax for that item. So I just want to make that explicit. If that correlation wasn't clear, this is shadowing task 2 quite directly. So we create the stack frame for total weight. We get a reference to the calling object in this, which is the player. The player called the object. And we're going to initialize a variable total, put that in the stack frame, initialize it to 0.0. No big deal. We've done that. We've done that for weeks and weeks. Then we're going to start this loop. We haven't seen a dashed box in a while, so let's get one of those in there. We're going to have a dashed box for our code block for our loop, which has an iteration variable, a looping variable obj object, which is going to iterate through the linked list. So we go through the linked list by following the reference, getting the first link in the list, and reading the value. That's going to be the first value that's stored in our looping variable. Then we're going to do total plus equals object weight. So this is our big question when it comes to inheritance and polymorphism. Object.weight. Which method is going to be called? We got 3 methods named weight in our code right here in our program. Which one is going to be called? It always depends on the type of the object that's calling the method, not the type of the variable. So object here is iterating over a list of game objects. So object, the variable, is of type game object, but we don't care about the type of the variable. So even though we're restricted to only what game objects can do, game objects do have a weight method. So we're going to call weight, but we don't go to game object. We follow the reference. So object refers to a health potion. So we use the health potion definition of weight. We always call the method of the type of the object, not the type of the variable. So because game object does define a method named weight that returns a double, we are allowed to call it, but we're not necessarily going to get the game object's weight method. We get the health potion's implementation of the weight method. So we are restricted. We had this big thing. I said polymorphism, there's one downside we'll start with. You're restricted to what the variable type knows. That's true for the definitions. But the variable, the type of the variable has a definition for a method named weight. But if it's overridden, we still do get the implementation of the inheriting class. So this is where we do get some power. We're not completely restricted to GameObject if we override methods. Now, if this didn't exist at all, and wait only existed in health potion and dodgeball, then we can't call this method because GameObject doesn't know that a wait method exists. There's no guarantee that that object has a wait method if it's of type GameObject. The arrows make you cry at home. Yeah. Same. Same. I don't want to do the arrows anymore. First of all, it's a pain in the ass to put them all on there. But it just clutters things up so much. So part of why these memory diagrams do look kind of messy is, one, the arrows, but we can stop doing those. But also the stack frames never are removed from the stack. So usually I used to remove these completely. They would just be gone. They wouldn't be on the slide anymore at all. But with these memory diagrams, we're going to cross them out. So everything just stays visually on the slide and in the memory diagram. So that does make them look a lot messier. But really, at this point on the stack, we have 3 variables, one that's about to get a return value, and then 4 variables down here. So there's not a whole lot going on the stack at the moment, but just visually it's cluttered because we have all these old stack frames that were destroyed. They're just crossed out. I'm not super thrilled about that, but I don't have a good answer to that either. Because when you're writing these in pen on your quiz, you can't erase things. Like, we can't have you do that. Yeah, blessed by memory diagrams. Yep, exactly. We can call wait because it exists in GameObject, but we do get the child class's implementations if they were overridden. So if a child class overrides a method, you will get that method from an object of that type. Okay, so what does this wait method do? Let's add a stack frame. The calling object, was this health potion at 200. And we're going to create a variable bottle weight. The weight of a bottle, which is going to be equal to super.weight. So even though we overrode the weight method, we still do have access to the super class's definition of the weight method through super.weight. So super is going to say, hey, I know I overrode this method, but go check out the super class, which is GameObject in this case. Go check out GameObject, and whatever definition it has for weight, call that. So we do still have access to this. Super.weight is going to call this method. We put that on the stack. This is still the calling object, which is still of type health potion. So if in this method I did... I got rid of my other method. We used to have object mass here. If I did object mass, it would still be the health potion's object mass because the calling object is still a health potion. Even though we jumped up to the super class, it's still a health potion. So unless we do super dot, it's going to be the health potion's implementation. So we return the base weight. So this dot base weight. Oh, no, base volume. I was hoping I wouldn't have another typo. That should say base weight. Damn it. That's on like every slide then, except the very first one. So this should say base weight. So base weight is 3.0. So that's what we're going to return, and that's going to be assigned to bottle weight. Stack frame returns 3.0 to bottle weight. Then we're going to do a little math. Bottle weight plus this dot volume, this dot mass per volume, this 200 volume, mass per volume plus 3. We're going to get that returned, which is going to be added to total. We're going to update that value and then iterate through again and do the same thing for dodgeball. So the next value, we're going to update our iteration variable. We're going to get the next reference in the list, 350. This time it's a dodgeball, so when we call object.weight, object is a dodgeball. So we're going to use the dodgeball's weight method. So weight here doesn't call any superclass anything, just straight up compute size times 5. This dot size is 4 times 5. We should be returning 20 and add that to our total. Add that to our total, which gets buried in all these arrows. I was looking at that like, do I curve all those arrows? Or I don't know. I'm just not going to do arrows next time, I think. Add that to total. This is the end of our loop. We're going to cross out our loop. That's the end of our method. We're going to return total. The very last expression in the method is total. So that's what's going to be returned. Return that. Kill the stack frame. Total weight gets 65. And finally, just print 65 to the screen. We hit the closing brace of our main, program ends. All right. So there's a lot of moving pieces here. If you can follow this whole example, you are doing fantastic, by the way. I would assume for most of you, there's at least something in there that you're still trying to wrap your head around why exactly this happened like this. And to the point where if I just gave you this program, you wouldn't be able to recreate this whole thing exactly at this moment. I would expect that to be where you're at. You would make several mistakes if you're trying to draw this whole thing just from the code. So if you can understand it all, let me just say you're ahead of the curve. You're doing fantastic. If there's something in there that you wouldn't be able to get from memory, drawing that whole thing, I expect you to not get it all. This is a lot of stuff in the past couple of weeks. 2 weeks ago, you didn't know what a class was. Now we have inheritance and polymorphism and all this kind of stuff on the screen. Multiple constructor calls. That's fast. That's a lot. So if there are questions. Is this in L2's lab exam? Hell yeah. Yeah, it's going to be. It might not be this complex. We'll try to keep the code simpler. But this idea that you have an abstract class that's extended by 2 other classes, and they have different methods being overridden, and which method you should call based on the type of the object, with at least one of them making a call to the superclass's overridden method. All of that, absolutely. There might be fewer lines of code down here. We might trim up wherever we can just to make it less tedious. But this concept of polymorphism, 100% is going to be on your quiz. Let's do this thing with 2 minutes left. I didn't do it right at 3:50. I'm trying to get to the lecture questions earlier. If you practice drawing polymorphism example that's on the slide, would you be in good shape? Yeah, it's an excellent way to practice, but if that's the only thing because for the quiz, you're going to get a program you've never seen before, and you have to draw the memory diagram. So if all you can do is copy the exact example in the slides, I wouldn't say that's everything. I think Latitude has a good answer for you on that one. You wouldn't be 100%, but that definitely is where you should start. Once you fully understand that example, then try. What I would try is tweaking the example a little bit and then trying to draw the new memory diagram and make sure you're able to do that. Yeah.
Is there any source that you can find online that gives you examples of questions?
Examples of not necessarily ones that will exactly line up with the way we're showing things. But if you do polymorphism examples, you'll of course get some. But I would say the ones in the example repo, I have some examples in the repo that I don't talk about in lectures, so you can find a couple extra there. And then Paul's lectures, like I explained earlier, and I don't know what else after that.